Okay, so the other important theorem that we use when we work with energy is the conservation of energy, right? So in that case, well, energy is conserved. You have initial energy have to be equal to final energy, and then you use that to solve problems. This, in many ways, is an easier theorem to work with, and so let's just remind ourselves a few key points. So it only works for conservative forces. Think of a force being conservative if there's no friction, right? If there's no ways to lose energy, then that is a conservative force. So if the force is conservative, so then the energy only depends on the initial and final positions and not on the way it went from initial to final. So, what are the typical conservative forces? Well, we are going to mostly we're going to work with gravity and springs, elastic forces. Those are the two main conservative forces. Friction is not a conservative force. So now the main theorem that we are going to work with is, well, you have initial energy, sorry, is equal to final energy. And this is equal to a constant and it never changes. So this is your initial kinetic energy, this is your initial potential energy, this is your final kinetic energy and your final potential energy. So if the force is conservative, then there is a potential energy associated with that force. So for gravity is mgh, that's your potential energy. For a spring would be 1 half k delta x squared. So those are the two potential energies that we are going to be using in most of the cases. So gravity. So gravity, we've seen how to use it. The potential energy is mgh, and we always have this freedom to choose what they call the datum, which is your reference point, your point of zero gravitational potential energy. That simplifies the problems a lot. So the other potential energy that is important is the elastic potential energy, which is 1 half k delta x squared. And that occurs when we have springs or anything that is elastic, like a bungee cord or something like that. So to solve these problems, well, you need to figure out your initial and final positions. Then you write your initial kinetic energy, your initial potential energy, final kinetic energy, final potential energy. Remember that potential energies would be gravitational plus elastic. And then you write that equation and you should be able to solve applying that equation. So let's look at an example here. We have this rod that has two rollers there. And so then there is a spring, there is also gravity. So you have that rod AB, it has a mass of 30 kg. And initially it is this angle theta here is 45 degrees. And the spring constant is 300 newtons meters. So you want to find the angular velocity when this angle is 0 degrees and the rod is at rest. So the picture might be deceiving. Imagine that this rod is going to land next to the spring somehow, so it's not going to be touching the spring. So we need to set a coordinate system and a datum, a reference point, so we choose it to be here. So that's the datum there and then that's when your potential energy is 0 because the spring is unstretched and, well, we're setting that to be 0. So this would give me an initial kinetic energy of an initial total energy of 0. What is the final total energy? Well, like 2. So when the angle is 0, so we can get the potential energy, gravitational potential energy is mg, and whatever distance it fell, which is 1.5 sinus 45 degrees. So that is the distance that it falls here. And the elastic potential energy, whatever it stretch, is 1/2 k, and then 1.5 minus 1.5 cosine of 45. This is how much the spring is stretched. So it's 1/2 k delta x squared. So then we can write that the potential energy is, the total potential energy is minus 127 Newton meters. Kinetic energy. So the rod is released from rest, so the initial kinetic energy is 0. So the final kinetic energy, what is that? Well, it's 1/2 30 plus, this is the translational kinetic energy of the center of mass, and this is the rotational kinetic energy of the center of mass, and here we have Ig, right? Sorry, is up to, this is Ig. So then we can write the kinetic energy, translation plus rotation, and we are done. So now we have that the kinetic energy, so we can write this equation, T1 plus V1 is equal to T2 plus V2. This is 0. This is 0. We already wrote this, and we wrote this. One more thing that we need to do is to, well, there is a simplification here. If you look at this equation, here you have omega, right? And you have the velocity of the center of mass. So we need an equation to relate both. So we are going to use the IC, the instantaneous center of rotation. So the velocity of the center of mass is the position of the IC times omega, and that gives me 0.75. If you don't remember how to find this, just go back to chapter 16 when they look at how to find the IC. And now we are done, right? So we are done. We can write T2. T2 is that, and then we can write our final equation and solve for omega 2.